Hello everyone, welcome to another section of the lecture series on measure theoretic probability. So today on lecture 2, we will be treating the sigma field generated by a set or class of sets. Remember, in our lecture 1, we left off some two questions we needed answers to them. So the first question was, do we have the empty set belonging to F? And 2, is it true that 3 star implies 3? So we answered these two questions in our lecture 2. So yes, indeed, by question 1, the empty set belongs to F, which is a field or a sigma field. So why? By condition 2, for F being a field or a sigma field, we have, that is, if A belongs to F, then it implies that A complements also belongs to what? F. So since we have the whole space belonging to F, then it implies we have its complements belonging to F, and the whole space or the sample space, the complement of it is what? Is the empty set. So by condition 2, we answer this question. Question 2. Is it true that 3 star implies 3? Remember, 3 was a condition for a field and 3 star was an extension for 3 to be what? A sigma field. So we knew that for condition 3 under field, we needed a finite what? Set. Then it implies that its finite union should also what? Belong to F. And by condition 3 star of the sigma field, we needed a countable what? Union for it to be what? A sigma what? Field. So we extend this. So our aim is to show that our countable union is equal to what? Our finite what? Union. So now, let's take A1 to be what? A. And for any n that is greater or equal to 2, we take an to be what? B. This implies that if you start from A2, A3, A4, A5 up to infinity, we take all of them to be what? To be B. Now, by countable union, then it implies that A1 union A2, A3, A4. Now our A2, A3 up to infinity, all of them are at B. Then it implies that if you union the same sets together, you get the same thing. So if you have A1 union B union B union B up to infinity, then we get what? A union what? B. This is a finite what? Union and satisfies the condition for what? A field. And this is also what? Satisfies the condition for what? A sigma field. Then it implies that 3 star implies what? 3. So yes, indeed, it is true that 3 star implies 3. We are good. Now, today on our lecture, we will be treating the sigma field generated by a set or a class of sets. So the analysis of probability problems usually begins on sets within some small class, that is maybe A, and through some operations, set operations, that is intersections and unions. You could actually take finite or countable intersections or operations of that. We may at a certain point be outside the initial class that we began with. So hence, we consider a class of sets that A, that I, contains what? The class in it, that's A in it. 2, that class is what? It's a sigma field. And 3, is in a certain sense as small as possible. So this is the sigma field that we have, the sigma field generated by a set. This is what we are about to actually treat in our lecture 2. Then we extend, then we talk about probability measures as well. So now, this class is the intersection of all sigma fields containing the class that we began with, that is A. And this is called the sigma field generated by A. And it is denoted by this symbol as we see, the sigma field generated by A. And by the name, it implies that that class should satisfy the conditions that needs to be a sigma field, or a class to be what? A sigma field. We have a question here to actually answer. But as we always do, we'll be answering these questions in our next lecture. So this question, if we let f theta be a class, be a sigma field for each theta, we want to prove that f, which is equal to the intersection of all these f theta, is a sigma field as well. So we will be answering this question, but just a gist or an idea or half of how the proof will go is that We want to let F satisfy the conditions to be what? A sigma field. This implies that we'll be checking all these three conditions. Then at the end, we prove that F is what? Is a sigma field. So by how we denote a sigma field generated by a set, the sigma field generated by A has these properties. 1. A, which is the initial class, should be a subset of the sigma field generated by what? A. And 2, the sigma field generated by A is what? It's a sigma field. This implies that it satisfies all the conditions that needs to be what? To be for a class to be what? A sigma field. And 3, if you have that class to be a subset of another class, and let's say that class that we are talking about, that's G. So if A is a subset of G and G is a sigma field, then it implies that the sigma field generated by this class is a subset of what? Of G. We have 3 questions we need to actually answer. We have other 2 questions we will find an answer to it. The first one is, if F is a sigma field, what is the sigma field generated by F? And 2, if we pick A to be equal to the whole space, then what is the sigma field generated by A? In our next lecture, we will find answers to these questions. Okay, so now to probability measures. But before we talk about probability measures, there's something interesting we need to actually take note of. A function mapping some class of subset of omega into the real line is called a set function. So when you talk about a set function, it's a mapping of subset of omega into the real line. So we build our knowledge on these set functions into what? Probability measures. So a set function P. So P now is a set function. We know the definition of what a set function is. So we define P on a field, that's F. It's called a probability measure if it satisfies the following condition. So note, we've underlined the field here, not what? A sigma field. So we are defining P on a field, not on a sigma field. So these are the conditions for P to satisfy to be what? To be a probability measure. We say for all A that belongs to F, then the probability of that set should lie between what? 0 and 1. And 2, if you pick the whole set, that's the sample space, its probability should be 1, and the probability of the empty set should be equal to 0. If you pick A1, A2 up to infinity, that belongs to F, and all these sets are mutually what? Disjoint, then if you have the countable union of it belonging to F, then the probability of the countable union of the AK should be equal to the sum of their individual what? Probability. And this is called what? The countable additivity property of what? Of P. So P satisfies these conditions, then indeed P is what? A probability measure. Alright. Note, there's something interesting here that we need to actually take note of. Remember, we define P on a field, not on a sigma field. So note, since F is a field, but not necessarily a sigma field, then we need to assume the countable union of AK belonging to what? To F. So we answer this question. Does the condition 3 for P to be a probability measure implies this? So here we consider what? A finite what? Union. So the probability of the finite union of the AI, is it equal to the sum? Is it equal to the finite sum of their individual probabilities for AIs mutually disjoint? So this is a question we'll be actually finding an answer to. Since we define P on a field, but in our third condition, we define P on what? On a countable union. Does it imply that 3 implies this? So we are going to find answer to this question in our next lecture. Thank you all and see you on the next lecture. Have a good day.